Okay, so on to question 3 on the practice final exam. And we've got a simple sort of cartoon of a generator here. Two electromagnets, or well, things that look like electromagnets but are just windings of conductor in this case. They're not being powered. That's where the power is being produced. And it's being produced because we're rotating this permanent magnet, and we'll get into all the details in answering the rest of the question. So, identify the armature of this generator. Does it reside on the stator or the rotor? Okay, so the armature is going to be on the stator, and it's going to be this coil of wire and this coil of wire. Okay, that's it. Okay, that's a pretty basic question on generators, right? If you remember the definition of the armature, where the power is produced in a generator or a motor or anything we're talking about, armature is always where the power is being produced. Generators produce electrical power, and because there's only one option here, right, effectively, because the permanent magnet is not a conductor, it's just a source of magnetic field, so the power must be produced in these coils of wire, or it's not going to be produced anywhere. So, sort of by process of elimination, you can get that. All right. So that's that'd probably be worth, I don't know, 9 points total. So that's probably a point in the whole grading scheme. And then B, is the output of the generator AC or DC? All right. So AC is our answer here. We don't see any of the two things that, or either, rather, of the two things that can produce DC from something that is quote unquote naturally AC because of the rotation of the magnetic field. So it can't be DC because we don't see any commutator and brush connection, right? That would be the kind where the rotor had the armature on it, and then you send the power through the commutator and to the brushes and to the external circuit. And but we already know that our armature is on the stator, so that can't possibly be. We're not using a commutator here. And the other method would be to have a rectifier on the generator, and it's possible that we could, we could certainly add one here after the output terminals, okay? But we're asking, as is this an AC or a DC generator? It's definitely AC for those reasons. No commutator and no rectifier. There we go. Okay, so a little explanation there. And that would probably be worth, along with the explanation, and hopefully explanation's always required, okay, unless otherwise stated, so, but hopefully on the actual final exam, I'll remind you of that there. Okay, but this is probably worth 2 points, one for the correct answer, AC or DC, and one for just saying, okay, well, why? Or how do you know that? All right, now, what would happen to the output of this generator if the speed of the rotor's rotation is increased, and why would this occur? Okay, so say we take our mechanical input. If we're doing something really simple, we could just take our hand on the hand crank on this rotor and really give it a spin. Okay, so we raise the speed of the rotor's rotation. Okay, so if we look at Faraday's law, go. Okay. Well, we're not changing the number of coils anywhere, so we're definitely not going to be, changing the construction of the generator. We're just spinning the magnetic field faster. But remember that this is the magnetic flux, or the number of magnetic field lines, and delta number of magnetic fields. I mean change in. All right, number of magnetic field lines over change in time. Okay, well, if we're spinning things faster, we're not actually changing the absolute number of magnetic field lines, but we are changing how quickly those magnetic field lines are moving. And so in the same period of time, we're changing the number of field lines in a larger way. That means that the magnitude, so this increases So the delta number of magnetic field lines, change in magnetic field, increases with rotor speed. Okay, and that means that the induced voltage also has to increase with rotor speed, right? Because if this goes up, then that has to go up. They're directly proportional. Now, the other thing is a little less obvious looking at the equation, but we have to remember what we learned about generators and how the rotation is linked to the cycle of electricity that occurs. Remember, in this simple kind of generator, we have voltage versus time, and it produces a sine wave that looks like this. And one cycle of that, so between here and here, say, okay, one cycle of AC corresponds to one rotation of the rotor, okay? Which is kind of nice, that one-to-one correspondence. And that means that if we spin this thing faster, we're getting more rotations in a certain period of time. And so we might get something that looked, let me switch colors here, okay? We might get something, like say we did it twice as fast, then we would get maybe something that looked like this, okay, in that same period of time. Something like that. So the whole wave would be taller because we already established that the voltage itself would increase with rotor speed, and it would be higher frequency, okay? So we would label this higher frequency. More rotations, more cycles. I didn't lay this out very well, but hopefully you can see all that. Okay, and so those two things would happen. We would have an increase in the absolute amount of voltage, so the peaks of these waves would be higher, and we'd get a higher frequency. And some version of this explanation, maybe not quite as much as I've gotten in here, would be acceptable to get the full, probably 3 points here. Okay, and then the last part, D, could this generator be run as a motor? If it can be run as a motor and the only thing you can change about it is the electrical source you attach to it, what type of motor must it be? If it cannot be run as a motor, please justify why this is impossible. Okay, yeah, kids are yelling out there. I don't know if you can hear that. Okay, so what we've got is a situation where, if we go back up to the diagram, say we attach a, let's start by just saying, okay, well, let's just attach a DC source. Okay, this is we should immediately recognize this would be a problem, because this would cause a constant current through these now electromagnets, because we're powering them rather than inducing power onto them. And I mean, the circuit's complete and all that kind of stuff, but that would just create a magnetic field going this direction. Well, depending on the direction of these windings, okay, but still, some magnetic field fixed in direction. And so this rotor would turn until it aligned with that magnetic field, but then the magnetic field wouldn't change, and so the rotor would just line up like a compass needle and then be done. Wouldn't act as a motor. So this is not an option. And instead, we can explore what we would get if we put an AC source in there, okay? All right, now if you did that, well, I think things would be good, at least, okay, because this is exactly the diagram we had for our introduction to AC motors, right? An AC source connected to two electromagnets with a permanent magnet in the middle. This is a very simple synchronous motor. And this would change the direction of current in the circuit, and that would cause the magnetic field on the stator magnets here, or electromagnets, to constantly shift back and forth in terms of its direction and in terms of how strong it was. And in a similar manner to what we looked at in the AC motors lecture, we would get rotation around and around and around. So yes, the answer down here would be yes, you could, if the input was AC, okay, and it would be a synchronous AC motor. Okay, so yes, you could if the input was AC and it would be a synchronous AC motor. Okay, and we basically answered the question because we're not saying it cannot be run as a motor, because then we need to justify it in a little more detail. And I talked through some of the reasons. I mean, you might say DC would not produce rotation, something like that. Maybe just a little bit of insight into your decision-making tree there, okay? But otherwise, good. So checky check. And this would probably be maybe 3 points for a total of 9 on the question. All right, so that's question number 3. Next video will be, as you might suspect, question number 4. See you soon.